So in this question, you were asked to consider the effect of wind speed on the timing of a sprinter in a 100-meter race. If a following wind is present, it will provide a small extra force, helping the sprinter to accelerate. With no following wind, a very simplified graph of the 100-meter sprint is shown below. Use the graph to show that v equals 10 meters per second. Okay, so this whole area, it's a velocity time graph, so the whole area will equal to 100 meters. So 2 lots of v. So the area of this triangle is 1/2 of 2v. And then if we add that to the area of this triangle, which is 9, just be careful, it's 2 to 11, so that's 9 seconds across. 9 lots of v equals 100 meters. So v plus 9v equals 100 meters. Therefore 10v equals 100 meters. Therefore v equals 10 meters per second. Calculate the resultant force on the sprinter when they are accelerating. So they're accelerating within this first section. So the acceleration is the change in speed divided by the time taken. The change in speed is 10 from a standing start. So they go up to 10 from a standing start. And then t is 2 seconds. So the acceleration is 5 meters per second squared. Then F equals ma. So it's 70 multiplied by 5, which is 350 newtons. Okay, so the next part to this one. I think we're done with it. There we go. So with the following wind, the sprinter achieves the same maximum speed of 10 meters per second, but has a slightly greater acceleration and reaches maximum speed after only t seconds, where t is slightly less than 2 seconds. The following wind reduces the time completed the time to complete the race by 10 milliseconds, shown on the graph. So calculate the time taken to reach the maximum speed. We have here, this is t, but this time we've got a little bit more work to do to get the values. So we know that this is still 100 meters, so the distance traveled is still 100 meters. This area can be expressed as 1/2 of v times t, and this area is so it's 10.99 seconds. Take away t, however long it took to get this value, all multiplied by v, and those two added together, those two expressions added together, will give us 100 meters. So 100 meters is 1/2 vt plus 10.99 minus t, all multiplied by v. So we'll multiply that out. And we have 1/2 vt plus 10.99 v, take away vt. We know the top speed is the same, so we've got 2 unknowns, but actually because we know what v is, we can substitute that in. So we get 5t plus 109.9, take away 10t, and then we just need to collect our terms. So we end up with, we'll move this to this side, so we get 5t on this side is equal to 9.9, and then we have t is 9.9 over 5, and 9.9 is 1.98, so 1.98 seconds. And as a check, because there's a bit of work for that for 3 marks, as a check, that is slightly less than 2 seconds. That's required. Calculate the extra resultant force to decrease the time of the race by 10 meters per second. So we can find the new accelerations. The new acceleration was slightly higher. So we've got that time to get the new acceleration. So the new acceleration, a is v minus u over t. It's the same 10 minus 0, but now it's 1.98. So we get the new acceleration. So 10 divided by 1.98 gives us 5.05 recurring. It's an intermediate step, so I'm going to leave that as that unrounded value. Then we've got F equals MA. So F equals MA is the 70 multiplied by 5.05, all recurring. So I'm just going to leave that in my calculation, multiplied by 70. That gives me the force, which is 353.53 recurring, but it asks me for the extra, and it's in bold to help me just point that out to me. It's the extra force. I need to just dig back through and find where I've put that previous page of working to find out what the force was before. I can remember it was 350 newtons. So the additional force is 3.5, and we've got two sig fig here. So I'm going to go with 3.5 newtons. So the extra force on the runner can be roughly approximated as 0.7 u squared, where u is the wind speed. So we're asked to find what wind speed will give us that advantage. So we've got F equals 0.7 u squared. So the F is 3.53, and again I'm going to use the unrounded value, divided by 0.7 is u squared. So I've got the unrounded value in here, divide that by 0.7, and I get that u squared is 5.0505, again recurring. I need to remember square root, that's a common thing to miss out. So u is 2.2 meters per second, and again it's 2 sig fig, just to be consistent. In reality, excuse me, the following wind has much less of an effect on the recorded time. State and explain one reason why the approximation is not valid. Now, the answer given in the mark scheme, I'm not entirely sure of, is that the runner will soon be running faster than this speed. But as someone who runs, you would then be running into less of a headwind. So the running itself has the effect of, although the air is still, you're having to push the air out of the way. It's not a big effect in running because the speeds are lower. Certainly would affect something like motor racing or a bike. So that's in the mark scheme. I actually think it's probably more to do with the leg speed of the runner is a limiting factor. So it's not just about how hard they can push off the ground, it's also how fast they can turn over their legs, so what the cadence of their legs would be. And I'm going to put in also they are soon running faster than 2.2 meters per second as well. So a bit of a compromise on that one.